Question 3.61 is actually a really challenging question. It involves many different steps to figure out the molecular formula of this compound. So we do a combustion analysis, so we burn a sample that's 0.44 grams, and from that combustion analysis we produce 0.88 grams of carbon dioxide and 0.36 grams of water. So probably initially you're already a little bit confused because how did we create more mass than what we started with? So in this combustion analysis of the CO2 and of the water, only the carbon and the hydrogen has come from the sample that we burned. Some of the oxygen did as well, but for a combustion reaction, you typically have your sample and you combine it with oxygen to produce the carbon dioxide and the water. So we can't directly say how much of that oxygen came from the sample and how much of that oxygen came from the oxygen that it was burned with. So what we need to do is take the mass of carbon dioxide, the mass of water, and find out how many moles were there, and then find out how many moles of carbon were there and how many moles of hydrogen were there. Then we can find the mass and then compare that to the initial mass to determine basically the remainder of that must have come from oxygen, and how many moles would that be? So for the first step, we need to do a little calculation to figure out moles. So I have 0.88 grams of CO2 and I have 0.36 grams of water. I need to figure out moles because I need to figure out of this 0.88 grams of CO2, how much is from the carbon and how much is from the oxygen. Same thing for water. So I know that for 1 mole of carbon dioxide, I should have 44 grams, and for 1 mole of water, I should have 18 grams of water. So grams cancel out, and I'm left with approximately 0.02 moles of CO2 and 0.02 moles of water. The next step, I want to convert carbon dioxide and water into how much carbon is actually there and how much hydrogen is actually there, because again, it's the carbon and hydrogen that came from my starting material. So I want to know how much I have of those. So I know in every 1 mole of carbon dioxide, I have 1 mole of carbon. The formula tells me that. In 1 mole of CO2, I have 1 carbon and 2 oxygens. Do the same calculation for water, and I know for every 1 mole of H2O, I'm going to have 2 moles of hydrogen. I'm going to have twice as much hydrogen because, again, the formula tells me that. So I've got 0.02 moles of carbon and 0.04 moles of hydrogen. So that's the first step. I found out how much carbon and how much hydrogen I have that came from the original sample. The original sample weighed 0.44 grams. I need to figure out the mass now of this much carbon and this much hydrogen and subtract that from the 0.44 grams to determine the remaining mass must have come from oxygen. So my 0.02 moles of carbon, I know that for 1 mole of carbon, I would need to have 12 grams of carbon. Do the same calculation for hydrogen, 0.04 moles of hydrogen. For 1 mole of hydrogen, I would need to have 1 gram of hydrogen. So I have approximately 0.24 grams of carbon, and I would have 0.04 grams of hydrogen. So my total sample, right, that I started with was 0.44 grams total, and that was carbon, hydrogen, and oxygen. So I'm going to subtract 0.24 grams that came from the carbon and the 0.04 grams that came from the hydrogen, right? to determine that the remaining mass, the 0.16 grams, must have been from the oxygen. And now I can do the same calculation to determine how many moles of oxygen I had in this sample. So I know oxygen, for every 1 mole of oxygen, I need to have 16 grams of oxygen, so that would give me 0.01 moles of oxygen. Now that I have moles of carbon, hydrogen, and oxygen, I can find the mole ratio. So 0.01 moles of oxygen, right? To find the mole ratio, I want to divide all by the smallest number. So I'm going to divide all of these by 0.01 because that's the smallest number here to give me a whole number ratio. So I divide 0.02 by 0.01 to get 2 moles of carbon, 4 moles of hydrogen, and 1 mole of oxygen. So now I have the empirical formula. The empirical formula is C2H4O1. I'm still not done yet because I need to find the molecular formula, and I know that this molecule weighs 132 grams per mole. So to go from the empirical to the molecular, I need to know, right, how many times do I have to multiply this empirical formula? To do that, I have to find the mass, the empirical weight of this formula. So I have 2 carbons at 12 AMU each. I have 4 hydrogens at 1 AMU each and 1 oxygen at 16 AMU each. So that gives me 24 AMU of carbon, 4 AMU of hydrogen, and 16 AMU, right? So this should weigh 44 AMU or 44 grams per mole. So to determine the relationship between the empirical formula and the molecular formula, I need to divide those two. My molecular formula is 132 grams per mole. My empirical formula, the smallest whole number ratio, is 44 grams per mole. Divide those through, and I get a factor of 3. So that means I need to multiply my empirical formula by 3 to determine my molecular formula. So C2H4O1, I'm going to multiply that by 3 because that's the relationship between the empirical and the molecular formula to come up with a molecular formula of C6H12O3. So this is probably one of the harder questions that we've seen all semester, only because they do not give you the mass exactly from carbon, exactly from hydrogen, or exactly from oxygen. You have to break down carbon dioxide and find out how many moles and the mass of carbon there. You have to break down water and find how many moles were there and the mass of hydrogen there from water. Once we are able to determine that, then we could determine the remaining mass must belong to oxygen. How many moles of oxygen did we have? And then we could find the mole ratio of those elements to find our empirical formula. After our empirical formula, then we could compare that to our molecular weight to determine what was the relationship between the empirical and the molecular. To see, I had to multiply the empirical formula by 3 to come up with the molecular formula of C6H12O3.